May 11th, 1940. North American Aviation Headquarters, Inglewood, California. The meeting lasted exactly 43 minutes, but those 43 minutes would fundamentally reshape aerial warfare. British Purchasing Commission representatives sat across from James Howard Kindelberger, President of North American Aviation, with a proposition that seemed absurd on its face. Can you design and build a completely new fighter aircraft in 120 days? The British needed fighters desperately. The Battle of Britain was weeks away. Curtiss P-40 Tomahawks were available for purchase, but the British found them inadequate, underpowered, and already obsolescent compared to German fighters. They wanted something better. They wanted it immediately, and they were willing to pay. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Kindelberger, in response, would trigger one of the most remarkable aircraft development programs in aviation history. Instead of simply licensing an existing design, he proposed creating an entirely new fighter from scratch. His chief designer, Edgar Schmood, had been quietly developing ideas for an advanced fighter. The British deadline was insane by any conventional measure. Fighter development typically required 2 to 3 years from initial design to first flight. The British wanted a prototype flying in 120 days and production aircraft within months after that. At that moment, the United States had no modern fighter aircraft in production capable of matching German Messerschmitt Bf 109s. The P-40 was already obsolete. The P-38 Lightning was promising but complex and expensive. The P-47 Thunderbolt was still being developed. Britain stood alone against Nazi Germany, and the Royal Air Force was weeks away from fighting for survival in the skies over England. What neither Kindelberger nor the British representatives knew was that their agreement would produce not just another fighter, but the aircraft that would achieve air superiority over Europe and make strategic bombing campaigns viable. The P-51 Mustang would prove that radical aerodynamic innovation could overcome engine limitations and that a medium-sized, relatively lightweight fighter could outperform everything else in the sky. The key to this performance would be a wing unlike anything flying at the time, a wing that seemed to defy conventional aerodynamic wisdom, a wing that military experts said couldn't work in combat conditions, a laminar flow wing that would make the impossible possible. The challenge began with fundamental constraints. North American Aviation had never designed a fighter aircraft. The company was founded in 1928 and had built trainers and bombers, but never pursued fighter development. Edgar Schmood, chief designer, was born in Germany, immigrated to the United States in 1930, and brought with him a thorough understanding of European aerodynamic research. Schmood had studied the latest work coming from the National Advisory Committee for Aeronautics, the NACA, which would later become NASA. NACA researchers at Langley Memorial Aeronautical Laboratory in Virginia had been investigating a revolutionary concept called laminar flow. Understanding this concept requires understanding how air moves over aircraft surfaces. Traditional aircraft wings create lift, but also create drag. A significant portion of that drag comes from friction between the wing surface and the air flowing over it. In normal airflow, the boundary layer, the thin region of air in immediate contact with the wing surface, is turbulent. Air molecules tumble chaotically, creating friction and drag. NACA researcher Eastman Jacobs had discovered that under specific conditions, the boundary layer could be kept laminar, meaning the air flows in, smooth, parallel layers with minimal turbulence. Laminar flow dramatically reduces skin friction drag. The theoretical benefits were enormous. A wing with laminar flow could reduce total aircraft drag by 20 to 30%, translating directly into higher speed, longer range, or better fuel efficiency. But laminar flow was extraordinarily difficult to achieve in practice. It required absolutely precise wing profiles. Any deviation from the ideal shape, even tiny manufacturing irregularities, would trigger turbulence. Surface roughness from rivets, joints, or paint imperfections would destroy laminar flow. Even dead insects splattered on the leading edge would disrupt the carefully maintained airflow. Military aircraft faced additional challenges: combat damage, weathering, field repairs, and operational wear all created surface roughness. Most aerodynamicists believed laminar flow was a laboratory curiosity with no practical application to military aircraft. Schmood disagreed. He believed that with sufficiently careful design and manufacturing, laminar flow could be maintained well enough to deliver significant performance advantages. When Kindelberger committed to the 120-day deadline, Schmood already had preliminary concepts sketched. He assembled a design team that would work 18-hour days, 7 days per week, for the next 4 months. The team included Raymond Rice, chief engineer, and Lee Atwood, chief of engineering. They commandeered a secure design space at the Inglewood facility and began work immediately. The fundamental design philosophy was radical. Instead of designing the largest, most powerful fighter possible, Schmood proposed the smallest, lightest airframe that could accomplish the mission. Reduced weight meant reduced wing area requirements. Reduced wing area meant reduced drag, and careful attention to drag reduction through laminar flow wings and streamlined fuselage design would maximize performance from available engines. The wing design consumed most of the engineering effort. Schmood selected a NACA 6 series airfoil specifically developed for laminar flow characteristics. The NACA 66-012 airfoil had been extensively tested in wind tunnels and showed excellent laminar flow properties under controlled conditions. But designing a complete wing structure that could maintain these precise profiles under manufacturing tolerances, combat loads, and operational conditions was unprecedented. The wing's maximum thickness was positioned at 40% of chord length, much farther back than conventional wings where maximum thickness occurred at 25 to 30%. This rearward positioning was critical for maintaining laminar flow over the maximum possible wing surface. The wing section was thinner than conventional fighters, creating challenges for fuel storage and structural strength. Schmood's team designed a single-spar wing structure with all fuel stored in tanks behind the pilot, creating the characteristic long nose profile that would become the Mustang's signature appearance. The wing's surface finish requirements were specified at levels never attempted in production aircraft. Rivets had to be flush, joints had to be perfectly smooth, and manufacturing tolerances were measured in thousandths of an inch. Military procurement officers were skeptical from the beginning. The Army Air Corps sent representatives to North American Aviation to review the proposed design. Their objections formed a lengthy list. The engine was inadequate. North American planned to use the Allison V1710, the same engine powering the P-40. If the P-40 was underpowered, how could the same engine power a superior fighter? The wing was too thin for sufficient fuel capacity. The laminar flow concept was unproven in operational aircraft. The flush riveting requirements would slow production and increase costs. The aircraft was too small to accommodate sufficient armament, and most fundamentally, North American had no fighter design experience. Why trust an unproven manufacturer with an experimental design during wartime emergency? Kindelberger's response was characteristically direct. We can deliver a prototype in 120 days. Can anyone else? The Army Air Corps could not answer that question affirmatively. Development contracts for other fighters measured timelines in years, not months. Britain needed fighters immediately. The British Purchasing Commission signed a contract on May 29, 1940. North American Aviation would design, develop, and deliver a prototype fighter aircraft within 120 days of contract signing. The design work proceeded at unprecedented pace. Engineers worked around the clock, producing drawings that went directly to manufacturing without the usual review cycles. The compressed timeline meant that design and tooling occurred simultaneously. Pattern, makers created wing molds, while engineers finalized structural details. Machine shops began producing components before the complete aircraft design was finished. Edgar Schmood drove the program with singular focus. Every design decision was evaluated against three criteria. Will it reduce drag? Will it reduce weight? Can it be manufactured quickly? These questions eliminated hundreds of conventional features. The fuselage was designed with minimal frontal area, making the cockpit cramped but reducing parasite drag. The radiator scoop was positioned beneath the fuselage, where exhaust heat could be used to create thrust, a technique called the Meredith effect that converted cooling drag into forward thrust. The landing gear retracted into the wings, but the mechanism was simpler than other designs, saving weight at the cost of slightly wider stance. The tail surfaces were proportioned for minimum area while maintaining control authority. Every square inch of surface area represented a drag to be minimized. By late August 1940, barely 90 days into the program, the first prototype was taking shape on the assembly floor. The aircraft was designated NA-73 by North American and would be called the Mustang by the British. The name selection story varies, but most accounts credit the British with choosing the name after seeing the aircraft's performance. The prototype, serial number 41-038, was completed in September 1940. The timeline was actually 102 days from contract to rollout, 18 days ahead of the impossible deadline. The aircraft was transported to Mines Field, now Los Angeles International Airport, for ground testing. October 26, 1940. Test pilot Vance Breeze climbed into the cockpit for the first flight. The prototype had been taxied and engine run but never flown. First flights are always dangerous, with unknown handling characteristics and untested systems. Lifted off, climbed to altitude, and spent 30 minutes evaluating basic handling. He landed and immediately reported that the aircraft was exceptional, faster than anything he had flown. Remarkably smooth and stable. Control response was crisp and precise. The Laminar flow wing seemed to be working. Over the following weeks, flight testing expanded the performance envelope. The Mustang reached speeds exceeding 390 miles per hour at 15,000 feet, faster than any American fighter then flying. Rate of climb was excellent. Range exceeded expectations by significant margins, but problems emerged. The Allison V1710 engine used a single-stage, single-speed supercharger optimized for low-altitude performance. Above 15,000 feet, power dropped dramatically. At 20,000 feet, the Mustang's performance degraded to mediocrity. At 25,000 feet, it was sluggish. For tactical reconnaissance and ground attack missions at low altitude, the Mustang was superb. For high-altitude bomber escort or fighter combat above 20,000 feet, it was inadequate. The British ordered the Mustang into production despite high-altitude limitations. The Royal Air Force used Mustangs for tactical reconnaissance, armed reconnaissance, and ground attack missions, where low-altitude performance was critical. American pilots flying Mustangs with the RAF were enthusiastic about the aircraft's handling and low-altitude speed, but frustrated by altitude limitations. Meanwhile, North American continued refining the design. The company built additional prototypes and worked through technical issues. The Army Air Corps, now the Army Air Forces, ordered small quantities for evaluation but showed little enthusiasm. American doctrine emphasized high-altitude strategic bombing, which required high-altitude fighter escorts. The Mustang's altitude limitations made it unsuitable for this role. The breakthrough came from an unexpected source. In April 1942, Ronald Harker, a test pilot for Rolls-Royce, flew a Mustang at an RAF base. He was astonished by the aircraft's performance below 15,000 feet and immediately recognized that the airframe's low drag would pair perfectly with the Rolls-Royce Merlin engine. The Merlin used a two-stage, two-speed supercharger that maintained power output to much higher altitudes. Merlin-powered Spitfires dominated at high altitude, but the Spitfire's airframe had higher drag than the Mustang. Harker wrote a report suggesting that combining the Mustang's low-drag airframe with the Merlin's high-altitude engine would create an exceptional fighter. Rolls-Royce executives agreed. They proposed a development program to test a Mustang with a Merlin engine. The British Air Ministry authorised 5 Mustangs to be modified with Packard-built Merlin engines. Packard Motor Car Company had licensed Merlin production for American manufacture. The modified aircraft were designated Mustang X. North American Aviation pursued a parallel program. The company recognized the Allison engine's limitations and began designing a Mustang variant using the Packard Merlin 61. This required significant airframe modifications. The Merlin was larger and heavier than the Allison. The cooling system needed redesign. The propeller required changing to a 4-blade unit. The fuselage structure needed strengthening. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The modified design was designated P-51B. The prototype first flew on November 30th, 1942. The transformation was dramatic. Maximum speed increased to 441 miles per hour. Service ceiling jumped to 42,000 feet. Rate of climb improved substantially. Range remained excellent because the efficient laminar flow wing reduced fuel consumption. The P-51B was faster than any German fighter at any altitude. It could outrun the Focke-Wulf FW-190 and the Messerschmitt Bf-109G. More importantly, it could escort bombers deep into Germany and fight effectively at altitudes where bomber formations operated. Army Air Force's leadership immediately recognized the P-51B's potential. Orders were placed for large-scale production. North American Aviation's Inglewood plant began producing P-51Bs in quantity. A second production line was established at a new factory in Dallas, Texas. The Dallas plant produced P-51Cs, identical to B models, but built in Texas. Production expansion required solving the laminar flow wing's manufacturing challenges. The wing's surface finish requirements were extraordinarily demanding. Traditional riveting techniques left raised rivet heads that disrupted airflow. North American developed flush riveting procedures where rivets sat flush with the wing skin surface. Manufacturing jigs held wing skins to tolerances measured in thousandths of an inch. Surface preparation required careful sanding and finishing. Paint application had to be smooth without runs or texture. Quality control inspectors checked every wing before installation, rejecting any with surface irregularities. The effort was worth it. Wind tunnel testing and flight testing confirmed that production P-51 seconds achieved significant laminar flow over approximately 30% of wing surface. This was less than theoretical maximum, but still dramatic improvement over conventional wings. The drag reduction translated directly into superior performance. By early 1944, P-51 Mustangs were arriving in England in large numbers. The 8th Air Force, conducting strategic bombing campaigns against Germany, desperately needed long-range escorts. B-17 and B-24 bombers were suffering catastrophic losses to German fighters. Unescorted bomber formations lost 10 to 15% of aircraft on deep penetration missions. Republic P-47 Thunderbolts could escort bombers to targets in Western Germany but lacked range for deeper missions. Lockheed P-38 Lightnings had range but struggled with reliability issues in European weather. The P-51 could escort bombers all the way to Berlin and back, maintaining combat effectiveness throughout the mission. The first P-51 escort mission to Berlin occurred on March 4, 1944. 668 bombers attacked Berlin, defended by fighters including hundreds of Bf-109s and FW-190s. P-51 Mustangs engaged German fighters throughout the mission. Bomber losses were dramatically lower than previous unescorted missions. The Mustang's impact on the air war was immediate and decisive. German fighter pilots found themselves outmatched. The P-51 was faster, had better acceleration, superior maneuverability at high speed, and could match or exceed German fighters in turning combat. Developed enormous respect and fear of American Mustangs. One technological advantage stemmed directly from the laminar flow wing. Reduced drag meant the Mustang maintained energy better in combat. When diving or maneuvering, conventional fighters bled speed quickly due to drag. The Mustang retained speed longer, allowing pilots to maintain initiative in combat. This energy retention gave American pilots decisive advantages in dogfights. The numbers tell the strategic story. From June 1943 to May 1945, the 8th Air Force lost 4,745 bombers in combat. During the same period, P-51 units claimed nearly 5,000 German aircraft destroyed. More importantly, bomber loss rates dropped dramatically once P-51 escorts became available for all missions. By spring 1945, the Luftwaffe was effectively destroyed as a fighting force. P-51 seconds roamed German skies at will, strafing airfields, trains, and vehicles. The strategic bombing campaign that had seemed unsustainable in 1943 became overwhelming in 1945, largely because P-51 escorts neutralized German fighter defenses. The P-51D model, introduced in mid-1944, incorporated the bubble canopy that became iconic. The earlier B and C models used framed canopies with limited rearward visibility. The D model featured a cut-down rear fuselage and teardrop canopy, providing 360-degree visibility. This was accompanied by 650 caliber machine guns instead of 4, and wing hardpoints for bombs or rockets. Production reached industrial scale. North American Aviation's plants in Inglewood and Dallas produced P-51 seconds at rates approaching 500 per month at peak. By war's end, total production exceeded 15,000 aircraft. The P-51 equipped most 8th Air Force fighter groups by 1945. It served in the Pacific Theater, the Mediterranean, and the China-Burma-India Theater. Top American aces flew P-51 seconds. Major George Preddy scored 26 victories flying Mustangs. Colonel John C. Meyer achieved 24 victories. Captain Don Gentile scored 19.5 victories, becoming a media celebrity. Lieutenant Colonel James Howard earned the Medal of Honor for single-handedly engaging German fighters attacking bomber formations. The aircraft's performance continued improving throughout the war. The P-51H model, introduced in 1945, was the ultimate development, with even lighter weight and higher performance. Maximum speed reached 487 miles per hour. However, the H model arrived too late for significant combat service. After World War II, the P-51 remained in service with the Air Force, redesignated F-51 under the new designation system. It served extensively in Korea from 1950 to 1953, primarily in ground attack roles. Straight-wing fighters like the F-51 were vulnerable to jet fighters like the MiG-15, but excelled at close air support missions supporting ground forces. Many nations purchased surplus P-51 seconds. They served in air forces across Latin America, Asia, and Europe into the 1980s. Israel operated P-51 seconds during the 1948 War of Independence. The Royal Australian Air Force flew Mustangs in combat during the Malayan Emergency. The Republic of China Air Force operated P-51 seconds defending Taiwan. The civilian warbird community preserved dozens of P-51 seconds. Today, approximately 150 airworthy Mustangs exist worldwide, with hundreds more in museums. The aircraft is featured at every major airshow. The distinctive sound of the Merlin engine and the graceful lines of the airframe remain instantly recognizable. The key figures in the P-51's development received varying recognition. Edgar Schmude continued working at North American Aviation through the development of the F-86 Sabre jet and the F-100 Super Sabre. He later worked at Rockwell and retired in 1968. He died in 1985 at age 84. His laminar flow-wing design influenced generations of aircraft. James Kindelberger led North American Aviation through massive World War II expansion. The company became one of America's largest defense contractors. Kindelberger served as president until 1948 and chairman until 1960. He died in 1962. The laminar flow wing concept that seemed so radical in 1940 became standard practice in high-performance aircraft design. Modern airliners use laminar flow principles to reduce fuel consumption. Military aircraft continue pursuing laminar flow for performance advantages. The research begun by NACA in the 1930s and proven by Schmood in the P-51 established fundamental aerodynamic principles. The story of the P-51's laminar flow wing is ultimately about refusing to accept conventional limitations. When military experts said laminar flow couldn't work in operational aircraft, Schmood proved otherwise. When critics claimed manufacturing tolerances were too demanding for production aircraft, North American developed processes to meet those tolerances. When skeptics argued that a medium-weight fighter couldn't match heavier designs, the P-51 outperformed everything. The success came from asking the right question. Instead of, "How do we make a more powerful fighter?" Schmood asked, "How do we make a more efficient fighter?" The answer was reducing drag rather than increasing power. The laminar flow wing reduced drag by 30% compared to conventional wings. This translated into higher speed, longer range, better maneuverability, and superior combat performance. The design philosophy was revolutionary. Conventional fighter design emphasized maximum power, heavy armament, and robust construction. Schmood emphasized minimum drag, adequate power efficiently applied, and careful optimization of every component. The result was an aircraft that seemed too small, too light, and too unconventional to compete with established designs. The P-51 proved that aerodynamic efficiency mattered more than raw power. A Mustang with 1,470 horsepower outperformed a Thunderbolt with 2,000 horsepower because the Mustang had half the drag. This efficiency allowed the P-51 to cruise farther, climb faster, and accelerate more quickly. The manufacturing achievement paralleled the design achievement. Producing wings with surface finishes precise enough to maintain laminar flow required developing new production techniques. Flush riveting had to become routine rather than exceptional. Quality control had to catch surface irregularities invisible to casual inspection. Workers had to understand that surface finish directly affected combat performance. North American Aviation transformed these demanding requirements into standard production procedures. Wings rolled off assembly, lines meeting tolerances that had been considered impossible just months earlier. The fact that over 15,000 P-51 seconds were built during the war proves that supposedly impractical laminar flow wings could be mass-produced with wartime urgency and workforce training. The strategic impact was profound. Without effective long-range fighters, strategic bombing would have remained unsustainable. German industry would have continued production. The Luftwaffe would have remained a formidable force. The air superiority that enabled D-Day and the liberation of Europe required neutralizing German fighters. P-51 Mustangs provided that capability. The tactical impact was equally significant. German fighter pilots who had dominated European skies found themselves outmatched by American pilots in Mustangs. The psychological advantage shifted. German pilots became defensive, trying to avoid American fighters while attacking bombers. American pilots aggressively hunted German fighters. The shift in initiative was decisive. The invisible achievement was the validation of advanced aerodynamics. Before the P-51, laminar flow was theoretical. After the P-51, it was proven. This validation encouraged aerodynamicists to pursue other advanced concepts. Swept wings, area ruling, supercritical airfoils, and other innovations followed because the P-51 proved that careful aerodynamic design could overcome seemingly insurmountable performance barriers. The legacy persists in modern aviation. Every commercial airliner uses laminar flow principles to reduce fuel consumption. Military aircraft pursue laminar flow to increase range and reduce radar signature. The fundamental insight that smooth, carefully shaped surfaces dramatically reduce drag remains central to aerodynamic design. The story matters because it demonstrates that radical innovation succeeds when visionaries refuse to accept conventional wisdom. Edgar Schmood looked at supposedly impractical research and saw practical application. James Kindelberger accepted an impossible deadline because he believed his team could achieve impossible things. Together, they created an aircraft that changed aerial warfare. The 120-day development timeline remains remarkable. Modern fighter development takes decades. The F-35 required nearly 20 years from initial concept to operational service. The P-51 went from contract to first flight in 102 days. This wasn't recklessness. It was focused urgency, combined with engineering excellence. The concentrated effort worked because the team had clarity of purpose. Design an aircraft with minimum drag, use proven engines and systems where possible. Accept higher manufacturing standards to achieve performance goals. These principles guided every decision. Features that didn't reduce drag or save weight were eliminated. Complexity that didn't enhance performance was rejected. This disciplined approach to design created an aircraft that was both revolutionary and reliable. The P-51 wasn't just fast, it was maintainable. Ground crews could service and repair Mustangs with standard tools and training. The aircraft was forgiving to fly with no dangerous handling characteristics. Pilots transitioning from other fighters adapted quickly. The combination of high performance and operational practicality made the P-51 exceptional. Many aircraft achieve high performance through complexity that creates maintenance nightmares. The P-51 achieved high performance through elegant simplicity. The laminar flow wing was sophisticated aerodynamically but straightforward structurally. Today, most people see P-51 seconds at airshows or in movies without understanding what made them special. The graceful lines and distinctive sound are impressive, but the real achievement was invisible. Those wings, carefully shaped to maintain laminar airflow, represented a triumph of theoretical aerodynamics applied to practical engineering. The transformation of aerial warfare that the P-51 enabled stemmed directly from Edgar Schmood's refusal to accept that laminar flow was impractical. He saw NACA research showing dramatic drag reduction and asked a simple question. Can we build a wing that achieves this in operational aircraft? The answer required extraordinary precision in design and manufacturing, but the answer was yes. That yes changed everything. It made long-range fighter escort possible. It gave American pilots technological advantages in combat. It enabled strategic bombing to succeed. It proved that careful aerodynamic optimization could overcome engine power limitations. And it established that supposedly impractical theoretical research could produce decisive military advantages. The engineers and workers who made the P-51 possible were doing what Americans do best, taking theoretical concepts and turning them into practical hardware, solving manufacturing challenges through innovation rather than accepting limitations, meeting impossible deadlines through determination and ingenuity, and creating weapons that were not just effective but superior to anything adversaries could field. The P-51 Mustang stands as proof that radical innovation succeeds when talented people refuse to accept that impossible means anything more than not tried yet. Edgar Schmood, answering whether laminar flow could work in operational aircraft, didn't conduct elaborate feasibility studies. He designed a wing and proved it through testing. This approach, building and testing, rather than analyzing and debating, characterized the entire program. When questions arose about manufacturing tolerances, North American developed production methods and proved they worked. When skeptics doubted high-altitude performance, Rolls-Royce installed a Merlin engine and proved it was exceptional. Action replaced discussion at every stage. The lesson remains relevant. Revolutionary achievements come from people willing to attempt what others consider impossible. The P-51 existed because Edgar Schmood believed laminar flow could work and designed a wing to prove it. Because James Kindelberger believed his team could design a fighter in 120 days and committed to that deadline. Because thousands of workers built wings to tolerances they were told were impossible. The aircraft that resulted from this determination, skill and refusal to accept limitations changed the course of World War II. It made strategic bombing viable. It established air superiority over Europe. It destroyed the Luftwaffe as an effective force. And it did all this through the application of a single aerodynamic principle. Reduce drag, and everything else becomes easier. That principle, understood and applied by Edgar Schmude in 1940, remains fundamental to aircraft design today. The laminar flow wing that made the P-51 revolutionary continues influencing how engineers think about aerodynamics. The proof that careful design can overcome power limitations guides modern efficiency efforts. When someone says a design is too demanding, manufacturing tolerances are too tight, or theoretical concepts won't work in practice, the P-51 stands as counter-argument. It was too demanding. The tolerances were too tight. The laminar flow concept was impractical, until Edgar Schmude proved otherwise by building an aircraft that dominated the skies and helped win World War II. That proof remains the most important legacy. Not the victories achieved or the enemies defeated, but the demonstration that engineering excellence, applied to radical concepts with skill and determination, can accomplish what seems impossible. The P-51 Mustang, with its revolutionary laminar flow wing, didn't just win battles. It proved that the right question asked by the right people produces answers that change the world. This is why the story matters. Not because aviation is interesting, though it is. Not because World War II was important, though it was. But because the P-51 represents a way of thinking about problems that remains powerful today. See the underlying principles, not the surface impossibilities. Apply theoretical research to practical problems. Demand excellence in execution, and never accept that something can't be done just because it hasn't been done before. In 120 days, North American Aviation designed a revolutionary fighter. In 30 months, they proved it could dominate the skies. In 5 years, they built over 15,000 of them. This was possible because engineers looked at theoretical aerodynamics and saw practical application. They refused to be constrained by conventional wisdom, traditional manufacturing limitations, or pessimistic predictions. They solved problems by asking not, "Why can't this work?" but "How can we make this work?" That question, applied consistently to every challenge, created an aircraft that achieved 437 miles per hour in level flight, escorted bombers 1,000 miles deep into enemy territory, and outfought every opponent it encountered. When Edgar Schmude sketched that first laminar flow wing design in 1940, he couldn't have imagined where it would lead. But in believing that careful aerodynamics could create decisive advantages, he articulated the confidence that made victory possible. The engineers who refined the design, the workers who built the wings to impossible tolerances, and the pilots who proved the concept in combat were all engaged in a collective achievement that changed warfare itself. They proved that laminar flow wings could be built, maintained, and operated in combat. They showed that aerodynamic efficiency mattered more than brute power, and they demonstrated that American engineering genius, when challenged, could accomplish what military tradition said was impossible. The aircraft are mostly retired now, preserved in museums or flown by enthusiasts. The engineers have passed away, but the method remains. The insight that careful attention to aerodynamic principles can produce revolutionary advantages lives on in every modern aircraft. And the confidence that engineering can solve seemingly impossible problems persists in every designer who looks at theoretical research and asks not, "Can we apply this?" but "How do we apply this most effectively?" That question, asked and answered at North American Aviation between 1940 and 1945, changed the world. It was not a question about weapons, or even about airplanes in the narrow sense. It was a question about possibility. Could a single-engine fighter escort heavy bombers from England to Berlin and back, fight superior enemy aircraft, and still have the range to return home? Every experienced pilot, engineer, and officer who had spent their life around aircraft knew the answer. No, it couldn't be done. The physics, they said, would not allow it. A plane fast enough to fight could not be large enough to carry the fuel. A plane large enough to carry the fuel could not be agile enough to fight. To most it was a contradiction, a beautiful dream destined to stay in the pages of design notebooks. But to Edgar Schmude and his team at North American Aviation, that contradiction was precisely the challenge. They didn't start with what couldn't be done. They started by asking why it couldn't, and then methodically set out to change the assumptions behind every no. Between 1940 and 1945, that spirit of defiance, disciplined by science and driven by necessity, gave birth to an aircraft that did what everyone said was impossible, the P-51 Mustang. Before the P-51, most aircraft were built through a process of incremental refinement. Designers improved what had already been proven: slightly more power, slightly better lift, slightly less drag. It was an empirical craft based on what worked before, tested through intuition, and validated by experience. But the rapid evolution of warfare in the 1930 seconds had begun to expose the limits of that approach. Air combat had become a domain of physics as much as bravery. Speed, altitude, and endurance were no longer qualitative measures of good enough. They were quantitative, mathematical variables that could decide wars. When Schmude and his engineers approached the problem, they brought with them the full weight of aerodynamic science that had begun to mature in university laboratories and wind tunnels across America. The central insight was that airflow could be controlled, not merely endured. Every curve of an aircraft's surface could be designed to reduce resistance, improve stability, and extract more performance from the same power. That principle, applied ruthlessly and systematically, led to the Mustang's most revolutionary feature, the laminar flow wing. A laminar flow wing was unlike anything that had flown in combat before. Traditional wings, with their thick, rounded, leading edges and rapidly changing airfoil sections, generated strong lift but also strong drag, the aerodynamic penalty of turbulent airflow. Schmude's design used a thinner, smoother profile that kept airflow laminar, meaning smooth and unbroken for a much greater portion of the wing's chord. The result was dramatic: less drag, higher speed, and better fuel efficiency. But this was not merely a theoretical exercise. Laminar flow wings were notoriously sensitive to imperfections. Even a rivet head slightly out of alignment or a rough patch of paint could trip the airflow into turbulence, erasing the advantage. Schmude's team therefore imposed manufacturing standards that were unprecedented for wartime production. Every panel line, every rivet, every joint was designed for aerodynamic cleanliness. It was an engineer's warplane, one that demanded precision not just in design, but in execution. The payoff was immense. At cruising speed, the Mustang could travel farther and faster than any fighter before it. Its range extended even further by drop tanks, finally allowed Allied bombers to reach the heart of Germany under continuous escort. The Luftwaffe, which had once relied on unopposed attacks against Allied bombers, was suddenly forced to face a fighter that could fight them on equal terms deep over their own territory. In this way, Schmude's wing didn't just make the P-51 fast, it made strategic bombing sustainable. It transformed the theoretical doctrine of air superiority into an operational reality. And in doing so, it changed the course of the air war in Europe. The laminar flow wing represented more than a technical achievement. It symbolized the triumph of scientific reasoning over tradition, the victory of calculation over convention. Before the Mustang, fighter design had been dominated by national styles and inherited dogmas. British aircraft favored maneuverability, German aircraft emphasized climb and dive, performance, and American designs often prioritized ruggedness and range. Schmude's approach broke with all of these. He believed the right answer would emerge not from tradition, but from mathematics. That mindset was revolutionary in its implications. It required a new kind of collaboration between theoretical scientists, test pilots, and production engineers. Wind tunnel data guided every design decision. but only flight tests could validate the results. The engineers didn't treat theory as an abstract exercise. They treated it as a living hypothesis, tested and refined in aluminum and air. This partnership between the theoretical and the practical marked the true birth of modern aerospace engineering. Every aircraft that followed, from jet fighters to commercial airliners, would owe something to the intellectual discipline forged in the Mustang program. Design by analysis, test by data, refine by iteration. Yet, behind the clean equations and aerodynamic curves, there was still a profoundly human story. Edgar Schmid, an Austrian-born engineer who had worked for Fokker and Messerschmitt before emigrating to the United States, embodied the transnational spirit of innovation that defined wartime industry. He was not driven by patriotism alone, but by a conviction that engineering excellence was a universal language, a way of thinking that transcended borders. He once said that his goal was to design a fighter that pilots could trust, fast enough to chase, stable enough to aim, strong enough to survive. And in that respect, the P-51 was more than a machine. It was a relationship between designer and pilot, built on mutual respect. The pilots who flew it from bomber escorts over Berlin to dogfights above the Ardennes understood that they were flying something extraordinary. The aircraft forgave mistakes, responded instantly, and carried them home from missions that would have been one-way trips in earlier models. To those men, the Mustang was more than the sum of its parts. It was a promise that science, when guided by courage, could make the impossible real. When the last P-51 missions flew in 1945, the aircraft's story did not end. It became the blueprint for an entire generation of post-war aviation. Its principles, low drag, high efficiency, precision manufacturing, became the foundation of the jet age. Even today, the laminar flow concept remains a goal for aircraft designers seeking ever greater fuel economy and performance. But perhaps the Mustang's most enduring contribution is not aerodynamic at all. It lies in the philosophy of engineering it demonstrated. The idea that progress is not a matter of luck or genius, but of methodical curiosity. The conviction that no requirement is too demanding if it can be translated into a problem of design. And the belief that innovation does not emerge from avoiding constraints, but from embracing them. These ideas echo far beyond aviation. They live in every field where people confront the boundaries of what is possible, from computing to medicine to space exploration. The Mustang story is not merely a tale of metal and engines, but of the mindset that turns impossibility into achievement. This is why Edgar Schmid's laminar flow wing matters. Not because it made the P-51 fast, though it did. Not because it enabled bomber escort, though it did. But because it represented a way of thinking about engineering challenges that remains powerful today. Apply scientific principles. Pursue excellence in execution. Accept demanding requirements as opportunities rather than limitations, and never accept that theoretical perfection can't inform practical design. Those principles, embedded in every square foot of P-51 wing surface, helped save democracy. They transformed an impossible requirement into a weapon that could reach across continents and win a global war. And they remind us that innovation is not born from ease, but from urgency, from the moment when someone looks at a contradiction and decides to solve it rather than accept it. The P-51 was not just an airplane. It was a manifesto written in aluminum and airspeed. It proved that imagination disciplined by science can change the world, and that impossible is just another word for not tried yet. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.